Hello everyone, welcome back to Introduction to AI Systems. Today we're going to cover a new topic of dimension reduction. And before going on to details about dimension reduction, we're going to see very basic statistics for machine learning. So before going on to details, let's first learn the difference between the statistics and probability. I guess you guys should see the difference between the statistics and probability, and the key difference is where we start from. So in the case of statistics, we start from data, and from data we build a model. So by using statistics, we build a model starting from data. That is statistics. And on the other hand, in the case of probability, we start from a model, and then by using probability, we produce or predict data by using probability. So that's the key difference where we start from. So in the case of statistics, we start from data, and in the case of probability, we start from model and produce or predicts data. And as a part of statistics, let's also learn the populations and samples. So these are the all part of statistics. And here, the terminology of a population includes all the elements from a set of data. So in the set of data, the population includes all the elements from a set of data. And a parameter is a quantity computed from a population, and two key parameters will be used. And the first one is the mean or the average, and the second one is a variance. So these two parameters are a very important quantity computed from a population. On the other hand, a sample is a subset of the population. So from the population, you take some data, and that could be a sample. So one or more observations could be a sample. And statistics is a quantity computed from a sample. So in this case, we don't compute the data from a population, but instead of it, we calculate from a sample from the observation, and that could be a statistics. So for that, the value, the quantity, the parameter value can be represented as a sample mean or sample variance or sample correlation. So you guys should see the difference between this mean, variance, and also sample mean and sample variance. And let's talk about multivariate statistics. Here, let's say X is a single data point, and X has a form of a vector. And then by collecting all these data points, we can construct this X vector, where its low vector represents single data points. So here, this one is kind of set of data point. So this could be a sample that we discussed earlier. So here we have m data points, so we have m samples. So that means we have m observations. Based on m observations, we collected a set of m data points, and based on that, we can construct the X. And by using these m observations or m data points, we can also calculate the sample mean, which is just nothing but the mean of the X single data points. And here this can be calculated by the by using average of the M data. And also here we can also calculate the sample variance, which can be calculated like here, and here calculated like here. And you guys should be see the difference between the sample variance and population variance. And here instead of using the n total number of population, we just calculate the sample variance using m observations. So here the difference is we just calculate the here we calculate the m based on m observation, and population variance is just the set of data. So here we use n instead of m. And let's talk about the correlation of two random variables. So here especially we're going to take the two random variables, two random scalar variables. So here let's say we have two random variables of x and y. And as we discussed earlier, sample variance for x can be computed like this expression. And here you should be noted that this sample variance can be computed from among the sample data set, not the entire data set. And in the case of sample covariance, as the terminology indicates, this sample covariance measures the covariance between two random variables of x and y. And here, instead of calculating the square of the multiplication of these two, the sample covariance can be computed like the x and y. And by using this sample variance and sample covariance, you can construct the sample covariance matrix, which is like this. So here, the first component is just nothing but the Sx, and the S2, Sxy, and Syx should be like this, and Sy should be located like this. And as you can see here, this matrix is symmetric because the covariance between sample covariance of Sx and y and Syx is equal, is the same, as you can see here. And here we can also use the sample correlation coefficient, which calculates the which can be computed like this. And so here the covariant correlation just measures the strength of linear relationship between two variables of x and y. So as the terminology indicates, this indicates just the simple linear relationships. And let's see a more detail about the correlation of two random variables. Here, for the simplicity, let's assume that x1 is smaller than x2, and x2 is smaller than the x1, blah blah, and xn is the largest. And also similarly for the y, y1 is smaller than the y2, y2 is smaller than the y3, blah blah, and yn is the largest. And for this given n pairs of n data set of x and y, you can construct the matrix of n vectors like this. And if the x and y has some relations like this, we can say these x and y two variables are statistically dependent, because here, as you can see here, when the x increases, the values of y also increases. So you can see some tendency like this. So here we can say that these two variables are statistically dependent. And also, if x1 and yn, x2 yn minus 1, and xn y1 has some pairs like this, so that means when you increase the number of x, the y values becomes decreased, here we can also say that these two variables are statistically dependent, because there is also some tendency like this. So here, when you increase the value of x, the value of y becomes decreasing. So here also we can see some tendency. So here, for these two cases, we can say that these two random variables are statistically dependent and their correlations are high. However, if x and y has some random selection pairs, that means here you can see no significant relation for x and y. So here we can say these two variables are statistically independent, and here we cannot say some significant tendency like this. So you guys should recognize the difference between the statistically dependent case and statistically independent case. So based on the previous result, we can conclude that we can define some correlation coefficient. So here, if the correlation coefficient is equal to 1, we can say the correlation between x and y has some close to a straight line relation, and if the correlation coefficient between x and y is equal to -1, this one is also close to a straight line, but in this case they have some relation. They have some relation like this. So when you increase the value of x, the value of y becomes decreasing. So here, if the correlation coefficient is equal to -1, +1 and -1, these correlation becomes close to a straight line like this. So these the value for the correlation coefficient just indicates how close to a linear line, but this does not indicate some slope or how they are related like this. So here, this one is also the correlate. In this case, the correlation coefficient is also 1, and for this line, this one is also the correlation coefficient is also equal to 1. So here, this does not include some information on the slope. So based on that, we can conclude that if the correlation coefficient should be the value from the absolute value of correlation coefficient should be the value from 0 to 1, and if this becomes to 1, then we can say this one is more linearly correlated, and if this one becomes to 0, then we can say this one is uncorrelated. So, and also please note that this does not tell anything about causality, which means this does not say some cause and effect. So if the correlation coefficient is 1 among x and y, that does not mean x causes y or y causes x. So we don't know some causality, but we can say they are related, somewhat related. So their correlation coefficient is 1, so they are closely linearly correlated. So that's the meaning of correlation coefficient. And finally, let's also learn what the covariance matrix. Covariance matrix just measures some covariance, and by using it, we can construct it as a kind of covariance matrix. So here, as you can see here, by measuring covariance and variance and covariance of the data, and here this one is not the sample covariance, and this one is the covariance of the entire population. So this one is the entire population, and here the diagonal component is the variance, and by using the n different variables, this one is the covariance. for the off-diagonal components are just covariance. So by just calculating all the variance and covariance, you can construct it as a covariance matrix. So that was the entire basic concepts of statistics that can be used in machine learning. And by keeping this in mind, let's go on to the new topics of unsupervised learning, and especially for dimension reduction. So before talking about it in detail, let's learn what the dimension reduction is. So the motivation of dimension reduction is very simple. The motivation is, can you describe high dimensional data in a simpler way? So that is just a very simple motivation. So the key idea for the dimension reduction is, we should lose too much information compared to the original data. But at the same time, we should describe high dimensional data in a more simpler way. So to find a low dimensional, this one is the very important key concept for the dimension reduction. So the objective is finding a low dimensional but yet a very useful representation of the data. So it should be low dimensional compared to the original data, but we should not lose too much information. So it should include very useful representation of the data. Then the why the dimension reduction or dimensionality reduction is important. Firstly, it should give insights into a low dimensional structures in the data, so it could be useful for visualization. And also, because it includes fewer dimension compared to the original data, it's less chance of overfitting, so it's better for the generalization. And also, in this case, because the dimension is small, it could speed up the learning algorithms. So most algorithms scale badly with increasing data dimensionality, but by reducing the dimension, we can speed up the learning algorithms. And also because the dimension is small, we can save our storage, so it does not require a high storage for saving data. So it can be used for data compression. So this one is the why we should learn and why we should use dimensional reduction. And you should be noted that the dimensional reduction is different from feature selection, and dimensional reduction is more like feature extraction. So the difference between the feature selection and feature extraction is like this. So for example, let's say you have some features features like x1 and x2 and x3 and x4 that and xn, and among these n features, if you just select these three features, that could be a feature selection, and that is not the same as dimensional reduction. Instead of it, dimensional reduction is more like feature extraction. So that means from these n features, you can extract some important correlated data like U1, U2, and U3 based on these X features. And by using this, you can reduce the dimension, and that is kind of feature extraction. So here you should note the difference between the feature selection and feature extraction, and dimensional reduction is more like feature extraction instead of feature selection. And by keeping this in mind, let's go back to the correlation between two random variables. And for the data with highly correlated, they may contain some redundant features like this. So let's say when you plot some correlation data between R1 and R2, for these two data, they are not highly correlated, so it has some low redundancy. But in the case of the highly correlated data, it includes high redundancy, because if you know some values for R1, it is very probably you can predict R2 based on some of these correlations. So this one is the basic idea for the dimension reduction for highly correlated data. And one of the most famous dimensional reduction algorithm is principal component analysis. So from now on, let me explain in more detail about principal component analysis. And before going on to detail, firstly, let's assume that let's think about very simple case. But here, simple case of x1 and x2, and its example x has only two features like x1 and x2. And consider ignoring the features of x2, for example. And then each two-dimensional example, x now becomes one-dimensional that includes only x1 information. Then when you see this plot, can you say that are we using much information by throwing away x2? The answer is no, right? Here, when we remove the information of x2, these data will becomes like this, only located in the x1 axis. And here, as the variance along the x2 is not that big, so most of the data is spread along x1 axis and very little variance along x2. So if you just remove the x2 components, we still does not lose much information for the data. On the other hand, let's consider the other case, and here this one also has the two features like x1 and x2, and in this data, let's also consider ignoring the feature x2 for its example. So this data also will becomes like this, located on the x1 axis. So now the data becomes one-dimensional x data. And here, when we think about are we losing much information by throwing away x2? And here in this case, the answer would be yes, because the data has substantial variance along both features. Like that means along both axes. So when you just remove the x2 information, here we cannot see x2 has some variance. In this case, compared to the previous case, x2 has some variance, right? Here the values is varying from here to here, so x2 has very large variance. So in this case, we cannot just ignore the feature x2. And here now let's consider a change of axis. That means the data are exactly the same, but here let's consider the case where the changes are when the axes are changed. So here, its example x has two features, but instead of x1 and x2, here we have u1 and u2. So by changing the axis of u1 and u2, this data also has two features like u1 and u2. And similar to the first case, let's consider ignoring the feature u2, for example. And by doing this, its two-dimensional example now becomes one-dimensional, only includes u1. And here, when we question about are we losing too much information by removing the u2 features, And the answer is becomes now no, because most of data is spread along U1 axis, so it has very little variance along U2. So this one is by doing so, the problem becomes exactly the same as the first case. So here it is okay to remove the U1 axis. So from the previous result, we can now conclude that it is important to see a proper axis for given data. So like for the second case, like this, when these data are featured as x1, x2, it is not easy to just remove out the x2. But in this case, for the same data, but at the same time, if we choose the proper axis like U1 and U2, it is okay to remove U1 and U2. It is okay to just remove the U2 out. So from that result, we can conclude that it is important to choose a proper axis for doing dimensional reduction. So that is the key idea for the principal component analysis. From now on, I'm going to call it as a PCA. So for given data, we need to calculate the projection onto unit vector. So the PCA is used when we want to projections capturing maximum variance directions. So here, by calculating here maximum variance directions would be the U1. So by capturing maximum variance directions, we call it as a principal components. So directions U1 of maximum variety in the data. So that is the principal components. And roughly speaking, PCA does a change of axis that can represent the data in a succinct manner. So for given these data, the idea is you need to calculate the variance, maximum variance direction, and that could be the principal components. And the idea is actually what we know in the linear algebra. Here it could be a eigenvector. So let's see how to calculate the principal components by using this graphical expression. So here, when you rotate this axis, you can calculate the variance. And here, when the axis like exactly the same as this line, we can see the data is mostly spread along this line. So that's how we calculate the maximum variance. So here we can say this. We can say at this point where the axis like along this, the data mostly separable or mostly spread along this axis. So that's the how to calculate the principal components, or to minimize the sum of squares. So that's it. So that's the idea of PCA algorithms. And from now on, let me explain in more detail about the PCA algorithm in more mathematical way. And before going on to detail about the PCA algorithm, we first need to pre-process for the data. So that means for given data of x, for the given x vector, let's say we have m observations or m samples. So by using these x vectors, you can construct the whole x matrix. And for these x samples, we need to shift and we need to rescale this data. So that means we need to shift mean to 0, and we need to rescale to make the variance becomes unit or becomes 1. So the first step is the shift to zero mean. So that could be very simply done by just calculating the mean original data's the mean, and by subtracting the mean, you can make the zero mean. So that by doing so, you can shift all the data into the zero mean. And the second step is optional, but should be optional, but you should do because it's optional, but it's nice. So the second step is rescaling. So this makes the data to have a variance with 1. So for that, we need to first calculate the variance, and by dividing it into the deviation, that is the square root of the variance, square root of the variance. So that could be the standard deviation or deviation. So by dividing the original data into the deviation, you can make the data into the rescaling by having to have variance becomes unit or 1. And the next step is finding the axis that maximize the variance. So for that, let's find some unit vector u such that maximizes variance of projections. And here we're going to take some assumption that m is equal to m minus 1 because we're going to consider very big data. So m is very close to m minus 1 for big data. So here we're going to use this assumption. So the variance of projected data, we need to calculate the variance of the projected data. So we need to calculate the variance of the projected data. And here, as you can see here, this one is nothing but the inner product of between the u and x vector. And because this one is the inner product, it can be commuted like this. And by rewriting these equations, by rewriting this, this is nothing but the u transpose x, x transpose u. And here we know that u vector is the unit vector, and this is unrelated to this summation. You can take this summation into this middle term. So you can rewrite this as u transpose times this. But here, when we look into this equation, this is nothing but the S, which is the sample covariance matrix. So by rewriting this equation, the variance of the projected data is nothing but the U transpose SU. And by keeping this in mind, let's rewrite this maximizing variance problem in an optimization form. So in previous slides, we have shown that our final goal is finding a maximized finding axis that maximize U transpose SU, where U is a unit vector, or if you rewrite the definition of unit vector, the inner product of the U and U is equal to 1. So this is our optimization conditions. But when we rewrite this, the objective function U transpose SU, in order to be maximized for these values, U vector, actually this one is just the inner product between the U vector and SU vector. And in order to be maximized for these values, U vector and SU vector should be in parallel. So that's to satisfy that condition, U vector should be the eigenvalue of the S vector, right? So by using this eigenanalysis where SU is equal to lambda U, we can rewrite SU as lambda U. And here we know that the lambda is an eigenvalue which is scalar, so this can be nothing but lambda U transpose U. And by using this condition that the U is a unit vector, this is nothing but the lambda. So by using this equation, our final goal to finding the U-axis that maximizes the problem is just nothing but finding the largest eigenvalue lambda 1 for covariance matrix S. So So here u is equal to u1 is the lambda 1's corresponding eigenvector, and u1 is the first. And by finding this eigenvector for the largest eigenvalue, lambda 1 is the first principal component which indicates the direction of highest variance in the data. So that is a very simple linear algebra. And alternatively, maximizing the variance problem can be understood as minimizing the sum of squared error. So let me explain why. So here we know that our problem is finding the eigenvalue or u-axis that maximize the variance. And here, when you think about the x vector and the projection of x onto this u vector, which can be written as the inner product between the x and u, then the error is x minus projection onto u axis. And here, by using this equation, is x squared, the xi squared is equal to u transpose x dot u squared plus ei. So by rewriting this equation, we can define the error, square error like this. And here, by rewriting this equation using by calculating the mean of this error for all the m data, this can be written as like this. And when you rewrite this, the final form, the final equation in the second term is nothing but the S that indicates the covariance matrix. So by rewriting the minimize the sum of square error, which is minimize sum of square error is exactly the same as minimize the size of the sample value minus u transpose SU. So u transpose SU. But when you see this equation, this minimizing the first term is constant for given x, which means this value is constant for given any samples. So and here by minimize minus means we should maximize this value, can minimize the whole this value, because it can be written as constant minus u transpose SU. So minimizing the sum of square error is just nothing but the maximize u transpose SU. So from that we can conclude that to minimize the sum of square error is nothing but the maximized variance. So either in this way, from this equation, you can solve the PCA problem by using the eigenvalue problem, and secondly by finding the minimize the sum of square error. Either way is fine, but either way is fine, so you can choose whether it is convenient for you. So from now on, let's do some dimension reduction from dimension n to k. So as I mentioned earlier, finding the dimension reduction using PCA is nothing but the finding the largest lambda of the eigenvalue. So the first step is calculating eigenvalue and eigenvector, and among them choose top k eigenvalue and its corresponding eigenvectors. So by finding these eigenvectors, the second step is projecting x onto the span of axis of u1 to u2 and uk. So by projecting these values onto the u-axis, you can find the new values for z, or G is equal to U transpose X. So here xi is by projecting these xi onto unit vector U, this value is nothing but U transpose X, which indicates the distance from the origin along U axis. So in a graphical representation, this can be understood like this. So from the original axis of x1 and x2, you can find the principal axis of u1, and by projecting these original data onto these u axis, you can find the projection onto unit vector u axis. Then from these point of view, by removing these u2 axes, you can reduce the dimensionality. So as I mentioned earlier, the important step is we need to pre-process data to have a zero mean and unit variance. So from the original data, you can pre-process data to have a zero mean and the unit variance. Then from these pre-processed data, you can calculate the eigenvalue and eigenvector so that you can find the principal axis. And by projecting these data onto two-dimensional to one-dimensional, you can reduce data onto you can reduce data into one. So this is just a pictorial summary of principal component analysis. And finally, let me compare two algorithms of linear regression and PCA principal component analysis. As we learned earlier, the linear regression is finding a best fitting model that represented the relation between x and y. So like this, we need to measure the error, all the error, and we need to find a best fitting model that minimize all the error. So that's the linear regression. But in comparison, PCA analysis is calculating the error, but in this case, you need to calculate error along the U1 axis instead of X1 and X2. So although these two graphical representation looks similar, the idea is totally different. Like so here, you need to calculate the distance from this to this. So you need to calculate along the y-axis, but here we are calculating distance, calculating error from the point from the data, and the principal component axis. So here we are calculating error along these axes. So that's the key difference. So you guys should recognize the difference well. So finally, let's implement this PCA algorithms in Python code. So for that, let's first generate some random data has the distribution like this. And as you can see here, the data has the zero mean, and when you see the distribution along this axis, it has maximum variance. But on the other hand, when you plot the distribution along these axes, the data has the minimum variance. So by using this, our objective is finding the maximized U transpose SU, where the U indicates the unit vector. So by calculating the covariance matrix, our first step is need to calculate the eigenvalue and eigenvector. So by using np.linearalgebra.eigenfunction, you can calculate the eigenvalue and eigenvector. And by finding the maximum eigenvalue, we are able to find the principal axis.
So by printing out the eigenvalue and eigenvector, here is the two eigenvalue, and these are the two. No, I mean these are the two eigenvectors. So yeah, and also by using scikit-learn, we can also use the PCA. We can also easily implement the PCA algorithms. So from scikit-learn that the composition algorithms, you can import the PCA, and by setting the PCA algorithm and by using the PCA.fit command, you can find the principal component analysis. You can find the principal components, and from that PCA.transform X is just the principal components, and when you plot this result, you can find the reduced projection onto U-axis, so you can reduce the dimension onto one dimensional. Yeah. So in summary, today we have learned basics statistics that can be used in machine learning, and from that we first learned the dimension reductions. So dimension reduction is kind of reducing the dimension without losing too much information. So the objective is finding a low dimensional but useful representation of the data. So among the dimensional reduction, today we have learned the first algorithms, which is a principal component analysis. So the idea of principal component analysis is firstly we need to pre-process data to have zero mean and unit variance. And among this data, you need to calculate the eigenvector, or here we call it as a principal. You need to calculate eigenvalue and eigenvectors and find the k among that, find the k largest eigenvalue, so that we can find the principal components. So by projecting this data onto these principal components, you can simply reduce data into from n dimension to k dimension. Yeah, so that's it for today's lecture, and thanks for listening.